Hey everyone, welcome back to The Explainer. Today, we're diving into a fascinating new research paper that completely challenges everything we thought we knew about the size of AI models. It's titled PaddleOCR-VL, Boosting Multilingual Document Parsing via a 0.9B Ultra-Compact Vision Language Model. We're going to unpack exactly how this research achieves top-tier results without the massive computational overhead we've all just kind of come to expect. zero point 0.9 billion. Seriously, in an era where tech headlines are constantly screaming about massive AI models boasting hundreds of billions or even literally trillions of parameters, 0.9 billion sounds almost like a rounding error, right? When you compare it to the massive scale of today's flagship models, you might think a system this compact couldn't possibly compete on complex tasks, but please don't let its size fool you. What this paper proves is that architectural efficiency can absolutely outmaneuver sheer brute force. So it really begs the provocative question for today's explainer. Do AI models actually have to be massive to be smart? It's basically a classic David versus Goliath story playing out right now in the tech world. And this matters deeply. Massive models require enormous server farms, exorbitant computing costs, and massive energy consumption just to run. If an ultra-compact model can go toe-to-toe with the heavyweights of the industry and actually win, well, that radically changes who can run advanced AI and where they can run it. Okay, let's dive into this. We're going to follow a quick roadmap. Starting with the document parsing challenge, then we'll meet PaddleOCR-VL, take a look inside its ultra-compact architecture, explore how it masters complex, multilingual elements, and finally, check out its real-world practical deployment.
All right, part one, the document parsing challenge, extracting data from complex documents.
Before we talk about the solution, imagine the sheer frustration of traditional data extraction. You've absolutely been there. You have a massive, scanned PDF. You're dealing with complex, nested tables. You're facing documents spanning dozens of varied global languages, or pages completely packed with dense mathematical formulas and intricate charts. The reason these are absolute nightmares for traditional algorithms is that standard systems typically just read left to right, top to bottom. They completely fail to understand spatial relationships. A nested table or a two-column layout instantly confuses them, scrambling the data and causing major headaches for anyone trying to automate document processing. Which brings us to Section 2, Meet PaddleOCR-VL, the ultra-compact fix. So PaddleOCR is built as a Vision Language Model, or VLM. As you probably know, this means it simultaneously processes and understands both visual information and textual information. But why is a VLM specifically necessary for document parsing? Well, in a complex document, the visual layout and the text meaning are inextricably linked. You can't just read the words. You actually have to see exactly where they are placed inside a table cell or a diagram to understand what they mean. The model has to see the page just as well as it reads it. The researchers in this paper propose that PaddleOCR-VL is a state-of-the-art, resource-efficient model designed specifically for this purpose. The crucial point here is that it completely defies the recent industry trend assuming bigger is always better. By being resource-efficient, we aren't just talking about saving a little bit of RAM. We're talking about a model capable of running entirely on consumer-grade hardware, instead of requiring a massive, expensive server farm. It totally proves that a highly targeted, specialized architecture can yield top-tier results. Let's crack this thing open in Section 3. Inside the ultra-compact architecture, the anatomy of a breakthrough. Now, what's really interesting about this architecture is how they structure the model into two highly optimized, interdependent components. Step 1 acts as the AI's eyes. It uses a NaViT-style dynamic resolution visual encoder. So instead of taking a high-resolution document and lazily squishing it down to fit a standard square input, which totally ruins small text, this dynamic encoder intelligently adapts to the document's actual shape and aspect ratio. It preserves critical visual details without wasting compute power. Step 2 is the AI's brain. It utilizes the ERNIE 4.503B language model. This incredibly lean language component processes that highly accurate visual data to make sense of the text. Because both parts are so tightly engineered for this exact task, they form a remarkably efficient pipeline. Moving right into Section 4, Mastering Complex Multilingual Elements, Global Parsing Capabilities. 109. That is the staggering number of languages this tiny model efficiently supports. It doesn't just work well in English, it's a truly global tool. Packing a global vocabulary and the grammatical nuances of 109 different languages into just 0.9 billion parameters is honestly a massive technical feat. It requires incredibly efficient training and masterful data curation, which makes this compact size even more impressive.
And it goes far beyond flat text. It excels at recognizing complex tables, intricate mathematical formulas, and detailed charts. Remember how we discussed that traditional OCR systems break down on these elements? That's because formulas and charts require distinct spatial reasoning. You have to intuitively understand superscripts, subscripts, and data points plotted on an axis. This model uses its vision-language integration to understand those spatial relationships seamlessly, tackling the exact pain points that normally break other parsing systems.
But don't just take my word for it. The researchers ran comprehensive evaluations on both widely used public benchmarks and their own strict in-house tests, and the results are pretty definitive. To quote the paper directly, PaddleOCR-VL achieves SOTA performance in both page-level document parsing and element-level recognition. To give that claim some concrete weight, the paper details how it significantly outperforms similar models in exact match metrics for complex table structures and formula rendering. It isn't just matching the heavyweights. In many specialized layout tasks, it's actually beating them.
Which leads us perfectly into our final section, Section 5, Real-World Practical Deployment, Fast, Cheap, and Accurate. When we compressed top-tier massive models against PaddleOCR-VL 0.9b, it's basically comparing a massive cargo ship to a nimble speedboat. While a massive model might take several seconds and incur high API costs just to parse one single dense page on a remote server, PaddleOCR-VL acts locally and swiftly. It boasts minimal resource consumption and incredibly fast inference speeds, meaning you can process thousands of pages locally in a fraction of the time and at a fraction of the cost. For you, whether you're a developer, a business leader, or a researcher, this means you get the absolute state-of-the-art accuracy of a massive model, but with a footprint small enough to run incredibly efficiently. Its strong competitiveness against top-tier VLMs successfully bridges the gap between high-level academic theory and everyday utility. It's fully ready for practical deployment in real-world scenarios right now. So as we see ultra-compact models like PaddleOCR-VL achieving such incredible things, it forces us to rethink our assumptions. Is the future of AI smaller, faster, and more accessible? Based on this research, the answer seems to be a resounding yes. Thanks for joining me on this explainer, and I'll catch you next time.